So coming up next, please welcome Kris Nova.
Hey, thanks for the intro, Thomas. And want to make sure everyone can hear me before I get started.
Yes, we can hear you loud and clear.
Beautiful, beautiful. I hope everyone's having a good day today. It's good to see everyone. And I kind of hacked the Zoom here. So I'm going to steal the screen share from you really quick, Thomas. And I'm going to share this screen. And if I did everything right, yes, I was able to successfully join 2 Zooms with the same user account. Okay, so let's get started. And let me adjust this really quick. There we go. That's a little bit easier on the eyes. Okay, so we're going to be talking about Falco with production eBPF. And I think Thomas was patient enough with me to let me change my talk 3 or 4 times over the past few weeks. And I finally settled with this one for a number of reasons, particularly because I think that the more I look at eBPF, I'm absolutely in love with the technology that makes it work that we were just talking about with Alexei. But even more so, finding a concrete use case for it and talking about what it's like having an eBPF program in production where people are using it day after day and the nuances that come with it and come with shipping it and that come with developing with it. And so I'm going to share a little bit of the human element of working with eBPF and what that's been like for us on the Falco project. So a little bit about me. I'm traditionally an infrastructure engineer by trade. I wrote a book called, or co-authored a book called Cloud Native Infrastructure with a great guy named Justin, and helped a lot with Kubernetes in the early days. I'm a maintainer of the Falco project, where I am fortunate enough to be supported by a fantastic group of individuals, most of which are based out of Italy. Lorenzo Fontana, he wrote or co-authored a book on BPF. He spoke yesterday. He's one of our main maintainers and pretty much taught me everything I know about BPF. I'm a hacker. I like to do things that I shouldn't do. And last but not least, I'm an alpinist, which I very much appreciate Thomas's Zoom background while he was talking. Okay, so like all good engineering talks, we begin our story with a question or a problem. And then we discover a set of constraints for that problem as we start to explore it. So the question, how do we instrument the kernel without a kernel module in GKE? And we're going to get into how this question was formed in the first place. And in order for you to understand how we got here, we're going to talk a little bit about this tool called Falco and what it does and how it works and how we even got ourselves in this situation of trying to understand how we're going to run this program without a kernel module and why we even need a kernel module in the first place. Okay, so here is my very high resolution logo of Falco, the Falco project. So just a little bit about Falco before we get too far into it. It's a runtime security tool. We'll jump into how it works and what it does in a moment. But on a political side, it's a CNCF project, meaning that it started out as just a regular open source project and was later donated to the CNCF by my current employer, a company called Sysdig. And we donated the project, and we advertised for it to be used for a number of things, specifically for what we call runtime security. In other words, securing a system at runtime instead of trying to take some sort of preventative action before the system comes online. I look at Falco very much like a CNCF-sponsored cloud-native surveillance system. And already, I'm sure most of your minds are going to kernel tracing and how we're able to do a lot of things that we do. So that's the political side of Falco. Let's talk about the technical implementation of Falco. How does Falco work? That's a good question. I've broken it down into 4 main things that Falco does, but let's really get into it here. So it rebuilds the state of the system at runtime. if you've ever used the command line tool Sysdig before, or like strace or dtrace, you're probably familiar with this concept of taking information that's happening in the kernel at runtime and bringing that up to user space somehow. Falco takes it a step further and uses the Sysdig internal libraries and builds an abstraction layer on top of the information that we're getting out of the kernel. So when we say rebuild the state of the system at runtime, what we're really saying is we're taking all of the system calls that are executed against the kernel, the arguments that are passed to them, and we're taking that and we're trying to rebuild what's currently happening. And we're also parsing other parts of the Linux kernel as well for different pieces of information, everything from process tables to various components that we're pulling out of memory. And we're putting all that together in an abstraction layer and giving that a well-known group of fields that you can then access and do things with. Falco asserts those abstracted fields against an arbitrary rule set. And if one of those rules are violated, we trigger an alert. The beauty of Falco is it uses what we call, and what most people call, kernel instrumentation, which is a fancy way of saying what I just said. We're tracing what's happening in the kernel. Furthermore, Falco takes other information and combines that with what's happening in the kernel to give us a higher level, more enriched view of what's going on in the kernel. So if we come down here to Falco components, I put together this diagram that will kind of explain what it is we're able to parse and how it's able to work. So on the left side of the diagram, we have arbitrary inputs into the Falco engine. And on the right side of the diagram, we have arbitrary outputs, what you can take out of the Falco engine. On the left side, we have the syscall events. This is kernel instrumentation. This is what's happening in the kernel, as well as other Linux information as well. We have what we call the container context, which is just context that we're building from something like the Docker socket or some sort of container level runtime. And we even take Kubernetes information as well. So Kubernetes meta information about what's happening on the host, what namespaces are running on the host, what are the names of the pods running on the host, arbitrary information, what do the labels look like, what do the annotations look like, even the audit information, who did what, when, and where. We take all this together and we put together this enriched stream of data, and we assert it against a set of rules. And then using arbitrary output, you can then take action. So naturally, a kernel module was our first approach here. And like Alexei just got done saying, there's obviously a lot that goes in with a kernel module, and there's some trade-offs when you look at kernel modules versus taking an eBPF or BPF approach, both of which kernel modules and eBPF are tightly coupled with the kernel itself. So there's a whole other exercise of evaluating that. That us maintainers were fortunate enough to get to go through and are fortunate enough to get to support. So anyway, that is Falco and how it works and what it does. And to give you a really quick concrete example, let's take somebody is calling an exec CVE system call. We want to get the arguments that are passed to it so we know what they're trying to do. And then we want to be able to say which container executed that system call and which namespace that container was running in. We could write a rule for that in the Falco engine, and then we could take that and we could shovel that over a gRPC socket somewhere and take action. Maybe it goes to Prometheus, or maybe it sends an email, or it does something. It's just a simple alerting mechanism. Okay, so that's Falco. Let's talk about kernel instrumentation. So again, we're rebuilding the state of the Linux system at runtime in Kubernetes, which is the primary use case for Falco. We have a single Linux system per node, and we have multiple nodes in a cluster. So we're faced with an interesting problem, which is not only do we want to assert security rules on each of the nodes, but we want a higher level way of amalgamating all that data together. So we're building this abstraction layer on top of Linux, and on version, what you can think of as version 1.0 with Falco, we were using a device driver, which we're going to look at here in a moment. If Thomas gives me enough time, I can actually show you what this looks like. And then we are using a kernel module to create this device driver. Obviously, there's some security concerns with this, as well as some other runtime concerns. Particularly, we're loading foreign software into a kernel. This is scary, especially if you're running in production, and especially if you aren't a kernel engineer, or if you didn't write the code yourself, or if you haven't had a chance to load test this beforehand. Furthermore, in order to load this driver, you need access to the host. And that's sort of a violation of the security node boundary in Kubernetes. And last but not least, you obviously need privileged access to load something into the kernel. So we're starting to walk down this path of there are some concerns with running a kernel module. So let's talk GKE. So we have some really notable constraints in GKE. Number one, you can't load a kernel module. That's just something that the systems that run GKE Kubernetes do not allow you to do. And if you communicate with them and you talk to them and see what their alternatives are, they suggest something like BPF as a solution to this. So you're not able to load kernel modules on the host. Furthermore, the Kubernetes API is an installation constraint, meaning if we want to install something on the host, we need to be able to do it dynamically at runtime. And finally, we want to be able to monitor all processes on the host. So something like ptrace wasn't going to be a viable solution right away because we needed to basically scan all available PIDs starting at the true PID one on a host system. So looking at these three constraints, it's pretty obvious that BPF is the natural choice here. It satisfies these and it gives us what we need to do what we want to do. So here we have discovered a very exciting moment in the history of BPF, a concrete production use case that eBPF is suited absolutely perfectly for. So that's what we did. We wrote an eBPF probe, a very large eBPF probe at that. And we emulate this device driver, but without actually using a Linux device. We use trace points and probe functions to replace the kernel module. So we're now able to trace various parts of the kernel at runtime. And the beauty of this approach was the rest of the system stays effectively the same. We basically were able to pull out the kernel module and replace that with a dynamically loaded eBPF probe. And we didn't really have to mutate any other parts of the Falco runtime system. It still observed data in the same way and still was able to get the same data it needed in the same way. And basically it just became another data source or another input for the broader system. One thing to note is this was ever so slightly less performant than the kernel module, which writing this in C and C++, this is a concern for a lot of folks, but it still did satisfy those main constraints that we had earlier. So there was a few caveats with eBPF, primarily the kernel. Which kernel you're running on has a lot to do with eBPF and I mean, even if you can run it at all, even if you can run it whatsoever. So the probe is compiled against the kernel, and here in a moment, if I have time, I'm going to actually compile a eBPF probe and we're going to run Falco with it so you can see exactly what that looks like. And I'm going to do a quick compare and contrast with Clang 9 versus Clang 10 with LLVM 9 and 10 and show how we're able to hit a runtime problem with BPF. I found this last night, which I guess is a really good opportunity for us to share. Like working on eBPF with newer kernels is exciting. You find new things every day, and it's really, really exciting for everyone. So it's a rare low-level new utility. And what I mean by that is not many people are using eBPF today. It's low-level, it's tightly coupled with the kernel, and it's new, it's exciting. You know, every kernel release, you're seeing new features, and LLVM and Clang are getting updates you know, very frequently. I mean, you go back and you look and you see commentary from 2019, 2020, and this is just a new and exciting space, and it's a really, really cool space to be a part of. So what we do is we dynamically load the BPF probe from user space. We wrote it in C. It's just probe.c, like Alexei was just talking about. It's compiled to an object, and we load it at runtime from the user space program itself, of course, with privileged access. Okay, so if folks have questions about that, feel free to let me know. And if not, I'm going to show 3 quick examples of Falco with a kernel module, Falco with BPF compiled with Clang 9, and Falco with BPF compiled with Clang 10, and just show the runtime impact of each of these. And I guess the beauty of the demo is it's going to be very boring. It's not going to be exciting. And that's kind of what we're trying to show here is the seamless nature of our approach of supporting this. So let's get started. So the first thing we have is I'm going to go, and I can zoom in a little bit here. It's probably a little bit easier. We have Falco checked out on my my local machine here, and you can see we have this build directory. And let's go and let's actually start compiling a few artifacts really quick. So let's go into build, and you can see here we have the driver directory, which is where we're going to compile our kernel module and our BPF probe. And if I witch clang, you can see right now it's in user bin clang. And if I list opt LLVM90, then you can see here we have a different clang in LLVM version 9.0. So we have both that we can use here. So let's really quick, let's make the BPF using clang 10.0, and then let's make the kernel module as well. I know we're compiling code during a keynote. This is just what I do. Thanks for bearing with me. Great. So we have the kernel module, and then we have the Falco user space binary. We'll compile this really quick. Doing its checks, and then once we get this, we'll show the different components, and we'll perform the same exercise with all of these. So while we're waiting for this to download, in fact, I already have it, but we can speed this up really quick. So anyway, we're compiling Falco, and we're going to get it up and running. And then to test it, all we're going to do is we're going to cat etc shadow here on my local file system, and that's going to trigger a Falco alert, and we'll be able to see how we're able to replicate the same functionality at the system call layer from both the kernel module as well as the BPF probe using clang 9. And I'm just going to cut this off. I've already got a Falco binary. I don't need to show you all how to compile it. If we witch Falco, you can see it's already here. I compiled this last night. So the first thing we're going to do is we're going to insmod this kernel module that we just built, which is here falco.ko. And if I list /dev and I pipe that to grep and look for Falco, you can see we have a device driver here on the left. We have Falco 1, and each one of these are for each of my CPUs here on my local computer. And if I now run sudo falco, you can see the kernel module is initialized. We're running the most recent version of Falco, and it's relatively boring. Nothing is happening. And if we open up a second terminal, drag this over, and we'll sudo bash, and we'll cat etc shadow. I'm not actually going to do this where you can see it, but you can see here, Falco did exactly what we wanted Falco to do. So now let's replicate this with BPF. So what we're going to do is we are going to sudo up, now running as root. The BPF probes are pre-compiled here in the Falco directory. And here you can see we have a BPF probe compiled with clang 10 and one with clang 9. And then this is just a symlink over to the Falco BPF object here. So let's remove the BPF object there, and let's symlink. We'll do clang 9 first. Falco BPF clang 9 to Falco BPF.o, this is just where the root user is going to expect to find the BPF object to dynamically load at runtime. So if we exit out of this and we run Falco with this Falco BPF probe flag, we're now going to be telling Falco to look for a BPF probe instead of a kernel module. And can't open. Why can't I open this? Falco BPF error. Huh. Interesting. I don't know why it's unable to open this. I might have, when I recompiled it, I might have gotten an error. Either way,
Hi, Kris, I'm sorry to interrupt. We're already a bit over into Q&A time. I now want to get at least one question in before we go over into the break. Maybe we can show the demo in Slack as well.
Okay, great. What's the question?
Irma is asking, does Falco need to somehow understand Kubernetes? And would it also work with a different container orchestrator?
The Kubernetes information that Falco gets is opt-in. It doesn't require Kubernetes to run. It runs on Linux. It does, however, have functionality to observe Kubernetes events and Kubernetes information, and also works with Mesos and a handful of other orchestrators as well. Basically, anything that runs Linux, Falco is going to be meaningful for, and then we can get more information based on the type of container runtime you're running on top of Linux.
Awesome. I know it's really hard to put this into 15 minutes. I know you tried really, really hard, but we are trying to stay on schedule. So first of all, thanks a lot, Kris. This was a fantastic presentation. Falco has really come a long way. Please give Kris a big round of applause in the Slack channel.